My name is Renato Golin. We're doing the EDG bridge to LLVM. Team is me, Evzen, Jim, and Grant is the head of everything. So I'll start by telling why EDG, why we're doing this bridge, and why it's important for ARM to actually do this. And then later I talk about a bit producing the IR and the things that happened, the good things and bad things that we came and saw these problems and reporting, because I'm not going to talk about that, yeah. ARM support. The third thing is ARM support is how good is the Clang LLVM, mostly with the Clang front end, LLVM support for the ARM platform. Let's go. EDG Front-End. So the main thing is, as you pointed out, there are already very good C front ends for LLVM. Why add another one? So the biggest reason is that we already use EDG in our compiler, and it has all the features we want for ARM, and our customers use these front ends for decades. So it's something that we want to keep compatibility. We want to see how the features that we already support are supported in the LLVM backend. Because using Clang, using LLVM GCC is good, even on ARM, but the tiny things we did because the customers asked for, these kind of things we want to know if that can be represented in LLVM IR and lowered to the correct code at the end of the day. So this is one of the big points, is that it's feature stable. Like the clients that used EDG front-end 10 years ago, they will be able to continue using these up to today, even though the backend is completely different. At least their code will still compile and produce decent code to newer processors. So, that's the other issue with GCC, is that we can't use GCC for everything because of the license, because the license GPL3 has this, the patent system that we can't just use. And so it's not just us. Lots of our customers can't just say, oh, I'm going to use GCC, because then they have to redistribute their own patents and everything. So, and Clang is still not perfect, of course, but none is. But it's, for the features we need, is not yet there. So that's why EDG. Now, what are the benefits that the LLVM community will get out of it? So one of the things is cross-checking the IR and the code generation against a different front end. That means it's different people doing the same thing again, just to make sure that the IR is not just made for the front ends that are there now. So we found that when we're doing some IR, we got some errors, and we saw how Clang did, or how LLVM GCC did, and we did the same way, and it worked. So that means for us that there is a vicious behavior, like because the backend was done when there was only one front end or two, and the front end behaves the same way. So if there's a new front end that doesn't behave the same way, doing the same thing, even though it generates good IR, it might break the backend. So it's good to have other people looking into these problems to get new code, new bugs, and we found problems in structures, unions, bit fields. There are long discussions in the list. We found code gen bugs that because of the ordered instructions. So, and we sent patches, and we sent patches for the runtime ABI. We found problems in Neon, in exception handling. All of this is good because it means that the backend is being rechecked, and then the quality, the overall quality increases. And we also tested there was a discussion in the Neon part in the list saying that the structures in the Neon part was due to compatibility, source compatibility with the ARM header. And then we try, okay, let's just ignore the structure for now and use direct vectors as it would be from GCC using the attributes for vector type, and it works. So it's another thing that we try to do differently that would take a time to make Clang and LLVM GCC, or I think just Clang, do it. But then because we did it in our front end, because it was faster, so that proves the point that Clang can then do the same thing, and it's easier and it's neater. So we also try to extend the code generation to do things that we do that Clang doesn't, because any Clang customers requested that feature, and because we have these and it's easy to add, we can just add in the back end or the middle end. And the last point is that some EDG users are already asking about the bridge. So maybe it's a good idea to have this bridge after all. So the things producing IR, I'm going to talk mostly about the bad things, because the good things, everyone knows how good it is. So the first slide is just like the general impression saying that it is good. It is very easy to generate the IR. The IR is very expressive, and it's easy to understand what it's doing. It's easy to see how the optimizations work on it. So you have the metadata, you can annotate whatever you want. The validation of the IR is very good as well. So it gets most of the errors, and if it doesn't get the asserts, get the rest. So also the LLVM codebase is very modern in C++ use and C++ capabilities. So it's a new code. It's different from other compilers. It's very hard to get to understand what it's doing. So, and it's very pluggable. So in that sense, it was very easy to write this bridge, because EDG has a very rich AST, and LLVM has a very rich IR. So it's very easy to make the connections between the two to get the expressiveness we wanted into the IR. And it also has good ways to debug, so it's dump and view graph while you're debugging. The LLVM is quite good. And the generated code quality is good. Like we did some tests to see the generated assembly or running programs, and the performance is good. The quality of the code generated is good. So we are very happy with using LLVM. But there are some differences, and most of the differences is because EDG is an AST that has to have all the semantic information, and LLVM is just an IR that has to have the instruction sequence information. So you don't need type system. You don't need a very complex type system in the IR, because it actually can make things more complex. So we had to do all the work of transforming all these type information that EDG had on types and structures and everything. So the sign information is one thing, because EDG doesn't have signed types. LLVM doesn't have signed types, EDG has. So we have to keep track of all these signs to do the casts and the comparison functions. So we need to keep a lot of extra information to make this, but it's not a problem. It's just one of the things we had to do, because the IR doesn't have this and shouldn't have this. But one thing that really was difficult was the alignment information, because EDG covers it all. It has type and variable alignment. The variable alignment overrides the type alignment, so if you have a specific alignment for a specific instruction, it aligns differently in the EDG, knows that. Also, structures and unions, the EDG gets the alignment perfectly correct. The problem is, in LLVM, structures and unions, actually unions, they become several structures. So the default alignment of the simple fields like integer and floating point and everything comes from the default alignment. But the special cases you have to do by hand. So structure is simple, it's just a structure with the types, but you have to get the alignment right. So what you do, you just put the alignment in instructions that will operate on those types, and it works. But the other thing is the unions and bit fields, they are massively complex. So when you're trying to get a union to initialize, so we have a static initialization of the union, and it's one of the fields, it's not the first field, so you have to create several structures that will initialize that field. So it's not something that it's easy. And when you cast it, for instance, to an array to do a mem copy, you completely lose the alignment information. So you have to always keep in mind that that array of sharp pointer is actually a structure, and it's a double, so it has to align to 8 bytes. So you have to keep these alignments in mind when you're doing this. So in the end, what we do is throw away completely the EDG alignment information and then recalculate, reconstruct later when we are lowering to IR. So that's not the best thing. C casting, or it's more like C type promotions and everything, actually. So EDG relies on this, but in LLVM there is no automatic casting, even for automatic promotions. So you have, when you're generating code, you generate a equal operator, and it has a cast between, or a plus operator, and it has a type promotion on this. EDG assumes, because the C allows you to, so EDG assumes that that promotion will happen anyway. But in LLVM, you can't just add an I8 to an I32. But it's not every case that you want to expand an I8 from an I to an I32. So there's some cases that you actually have to do something else. So we had to come up with several non-trivial helpers to avoid bloated EIR with lots of casts back and forth. And actually, doing these casts, these automatic casts, saying, whenever we have an I8, make it an I32 and add, that actually generated bad IR. So it caused many failures in being too permissive or just getting it wrong. So it took us a while to be completely auto-cast free, but it was worth it. Now, there's a good matching between the two. C++ support, although Clang C++ support is very good now, but EDG C++ support is complete. It supports completely all the standards. So, and the good thing is that it lowers the C++ into C. It still keeps lots of the other information that you can't represent in C, but the structures and the virtual functions, everything becomes structures and arrays with pointers, function pointers, and it creates all the thunks and all the specific kludge to make it work. So this is one thing that's quite good. The static construction and destruction the model is identical to LLVM, so it was just follow the same path. It was very easy. The big problem was exception handling, because there is no ARM exception handling yet. So it's one thing we was discussing in the other session. The EDG storage class, which is kind of the linkage type, but it's not exactly. So you have to take into account the storage class to export the correct linkage type and some other specific things, like if this is VTT or this is a type information and is of storage class foo, use the linkage type bar, otherwise. So it was very complex mapping between the two. It requires some magic, some things we just tested and got it by iteration. And the explicit allocation is an interesting, because when you see in Clang output, it explicit allocate every parameter. And then we thought, this is not really necessary, because you don't have to do these things. So if you already have the parameter and it's already in memory or something, you don't have to do these things. But then you actually do, and because of things, for instance, the thunks, I got a thunk that got the parameter, changed the parameter in the return, which means I didn't have time to store the altered parameter into memory or into an alloc variable and then to return that. So then these kind of things, it's easier if you do the explicit allocation of every single parameter. And then in the end, the backend just completely removes all the useless. So there's no point in trying to save this in the front end because the backend already takes care of it. In structures, we have one little problem, which is when you're passing the structure by val, what you should do is pass or allocate a local structure, pass the address, and then later on copy again. The thing is, this is the normal trick. In Intel, it works out of the box. In ARM, in some cases, it did work, but not all of them. And then we tried to see what Clang was doing, and it was casting the structure to an array and passing the pointer to the array instead of pointer to a structure. Because there was a specific rule in the backend saying, if this is an array and it's being passed by a pointer, it's probably a bival, and it has the bival keyword, then do this specific kludge that is required to make it work in the ARM ABI style. But there was not a single, a specific rule that for structures. So instead of implementing the same specific rule for the structure, it just cast as an array. And that's what we did in the end. So the thing is, again, you lose alignment, you lose lots of other things that you change the signature of the function. So it's not the perfect. It would be good if we could use the struct by val directly, because it makes more sense. The return value is the same thing, because if you return the structure, you will become the first argument of the function, and because it's a by val, then you'll be a pointer, so you get in the same problem again. Unions. There are lots of talks about unions in the mailing list. And the big thing is that the number of workarounds to make it conform to the C++ standard is huge, because it's hard to do it in the back end, I understand. But then what happens to the front end is that if you have a union with 10 fields and for a reason you initialize 10 unions each of the fields, you have to have n structure types for n initializer. So a union int A, double B, and you initialize in one union the A and the other the B. You have to have two structures, one which is an int with a padding to be the same size of a double, and the other is a structure with a double. So you initialize it and then how do you match these two types, because they are exactly the same. So you should be able to copy a structure that has an int and a padding to a structure that has a double. So you have then to cast to I8 arrays, mem copy and back. So it starts getting ugly when you have big unions and weird unions. It starts getting really, really ugly. So again, keep track of all the alignments and everything, because once you cast to I8 arrays, you can lose completely the alignment. So yeah, that's the thing. Implementing in the backend might require more changes than it was to do this, which is you have to do all the changes, but you have to do all the changes in all the targets simultaneously, because if you put a union array and then the ARM target doesn't support this union type, then how can you use it? So you can only use the union type with the backends that actually understand this. So to make this move, I understand why it hasn't been done yet, because to make this move, you have to change all the targets to understand the union. And it's not an easy task. Bitfields. Bitfields was a bit more dark, because zero-size bitfields is something that it's in the standard, and the standard tells you the bitfields finish the packing of the previous field. But what happens if there was no previous field? Normally, because the standard doesn't say anything, you just ignore. But we don't ignore. We do a clever thing. You say, it's a structure with a char A, so this is 1 byte structure. But because you said there was a bit field, zero size but type int, that demands the alignment of the whole structure. So that means this is a structure that only accepts a char, but is aligned to 4 bytes. So that's a specific thing that if you see GCC for ARM also understand this, because probably somebody from ARM told them, oh, we do this, and they say, yeah, okay, and they did it. But of course, this doesn't exist in Intel, and Clang is not doing this for the ARM backend. So it's these kind of things that we pick up that Clang probably would never pick up, because it's the kind of hidden things that you have to read the whole PDF. And probably, the guys that wrote it, if you didn't write that chapter, you wouldn't know this kind of things. So then that's our idea, maybe introducing I0 integer type, but not today. So exception handling, there was a big discussion about exception handling, and it has not yet been implemented, but there are plans to support and lots of people working on it. So hopefully in the near future, it will be there. I tried to change the dwarf exception class to conform to the exception handling API for ARM, but it wasn't quite a good idea because I completely destroyed the dwarf exception for Intel, and I couldn't get it to work on ARM. So it was like a no-go. I just gave up and say, no, let's wait for it to get properly implemented, because we have these backend, and the backend only prints ASM, and we have to use gas to read this. But code sorcery gas is changed in a way that it doesn't understand what the normal gas for Intel would understand as an exception handling table. So then it just didn't understand. So we could implement in EMC, which is, I think, the idea, or we could write dwarf exceptions directly to ELF, which is another thing that we might even support both, because that would be good to have this interoperability between the standard dwarf exception and the ARM exception. Neon. Neon is a good topic because that's the kind of thing I'm doing right now. There's one, I've noticed that the table gen for the Neon instructions is complete. As in, it has all the instructions and all the pattern matchings, but I'm still working on one by one to make sure how they are represented in the IR. So we have mainly 3 types. Until 2 weeks ago, I only knew about 2 types. So one of them is pattern matching. So if you have like a zero extended variables being added, that becomes a VAdd long. If you have, and the other one is an intrinsic. So if you have specific call to that, it becomes a VH add. But 2 weeks ago, I discovered that there's a third type, which is an intrinsic call plus a pattern match. So, and that's a clever thing from the table gen, because the table gen, you can pattern match whatever you want. So you can pattern match instructions, you can pattern match function calls or built-ins or whatever. So this is how it works. Unfortunately, in our case, it probably won't happen for the other backends, but in our case, our header didn't quite reflect that. So Clang header is perfect. It just reflects every single type of these, and you just lower the function as if you lower any other function, it just works. But in our case, it's not like that. We have lots of built-ins, and so we have to keep tracking, is this instruction this, and is it an extending, is it this, that, so it got very complicated, but it's nothing to do with Clang or LLVM, it's the way things interoperate between them. And the structure versus vector in the Neon type representation, that source compatibility is important, but the front end can recognize and see that that structure is actually a Neon, because the Neon structure, or the ABI says that it has to behave like a structure. It doesn't have to be a structure. So the mangling has to reflect the fact that that was a structure, but it doesn't have to be a structure. So you could use GNU vector types and mangle it as if it were structures with the correct name in the Neon format, and it would just be just as good. So we do that. We recognize that the structures are actually Neon types, and we just transform them into IR vectors. So we had some suggestions. Some of them we talk in the other talk in the both sessions, which is maybe add target attributes in the IR header. This is something of a discussion. It's not really crucial, and we can do it other ways with global variables, special global variable just for ARM. But we need to represent this in the IR, because the build attributes are not just a description of the target. They are actually the differences that you want the target to be. So if you say that V4T accepts thumb, you don't have to say that, because that's what V4T is. But if you say that you're compiling for V4T, but you don't want thumb, then this is a build attribute. It's saying I don't want, even though I support it, I don't want it, because then you don't link against libraries that have them, because, I don't know, I don't want it. It's faster or something else. So the other thing we also discussed in the meetings is add more validation to the debug information. And this is a good idea, and it was agreed. I think we should do this. It's because the MD node pointer is too opaque to do the validation, because it's just a pointer with something, and you can't say what something is. So the helper classes have to actually do some validations. So the other thing is we tried actually to propose, but we can't just get into because it's too big, unions and bit fields. Unions is a big thing. It was removed from 2.8, and I think there was a guy that was trying to implement this himself, but I'm not sure it's actually going too far. Bit fields, there was another proposal to use IN as a bit field, but then you have to align for like as an int. So still some discussions. It's a good idea to, it'd be good to do this so then the backend could understand better. And make the same special case that the backend does for arrays by val, do it a structured by val. Architecture support, I'll go really quick on this because we tested Drystone on all supported architectures that Clang list as supported architectures, and it works fine. We got even specific instructions for V6M, so it was really good. We tested hard FP, soft FP, Neon, and it just works fine. Our internal tests, they run mainly on 70DMI and Cortex-A8, so we got the two edges of the range, so at least we know that it's doing fine in most cases. And the Neon's fine, very good. We got almost all intrinsics get compiled to the instructions correctly. We reported some bugs, but minor bugs. And still missing, well, EABI, RT support, FP. We sent some patches for the floating point and the REM, the remainder memset. And there's still some things, the exception handling and the elf writing are the two main things we want. And maybe an ARM assembly dialect, if we can plug in into MC, would be nice to have. Thank you very much.